So, you see a robot arm glide through the air. It descends, gently closes its gripper on a box, lifts it up, and places it perfectly on a target. It all looks so smooth, so effortless, right? Almost like it's alive. But what is really going on under the hood to make that happen? Well, let's deconstruct that seemingly simple action and find out.
And that's the million-dollar question, isn't it? Because that one fluid motion you just saw, it's not one thing. It's a carefully constructed stack of plans, calculations, and physics simulations, all firing off in perfect sequence. So today, we're going to peel back those layers and see exactly how a robot pulls off a successful pick-and-place.
Okay, so at the very top level, the robot isn't just winging it. It's following a strict script, a master plan. The best way to think about it is like a choreographer's notes for a very precise dance. In robotics, we call this a state machine, and it dictates every single major step of the entire operation.
And here are the key moves in that dance. You see, the robot doesn't just go to the box. First, it plans a totally collision-free path to a point above it. Then, it executes that approach. Only after that does it descend to actually grip the box. Each of these phases is just one part of a much larger 11-step state machine. It's this complex ballet of code and steel.
So the state machine tells the robot what to do, like move to the approach point. But it doesn't say how to do it. How does the robot figure out the exact angles for all 6 of its joints to get the gripper to that perfect spot in space? Well, that's where the math kicks in.
This is the job of something called inverse kinematics, or IK for short. You give the IK solver a target for the gripper, and it works backward to find all the right angles for the shoulder, the elbow, the wrist, all of it. This system uses a really robust method called damped least squares IK. You can think of it as iteratively nudging the arm closer and closer to the target with a clever damping term to make sure it doesn't get stuck in any awkward poses.
And here are the results of all that math. 4 absolutely critical waypoints. You've got a pre-grasp pose, a safe 15 centimeters above the box, and then the actual grasp pose right at the center. But just look at that accuracy. The solver gets the gripper to within 1/10 of a millimeter of its target. I mean, that is some serious precision.
All right, the arm is in the perfect position. Now for the main event, actually grabbing the box. Let's zoom in on the business end of the robot here, the gripper. This isn't just a simple clamp. Its design is packed with some really clever engineering to make grasping reliable.
Every gripper has a specific physical range. This one, when it's fully open, its fingers are 98 millimeters apart. When it's fully closed, that gap is 38 millimeters. Now this is a supercritical design choice. Our box is 40 millimeters wide, so when the gripper closes to 38 millimeters, it's guaranteed to make solid contact. Think about it. If the minimum gap were, say, 41 millimeters, it would just close on empty air, and the whole thing would fail.
But the really crucial part is how it gets that perfect symmetrical closing motion. Instead of needing 2 separate motors and 2 different commands for each finger, there's a simple but brilliant trick at play. An equality constraint in the model forces the right finger's joint to always perfectly mirror the left's. This just cuts the complexity in half. You get 1 command, 1 motor, and 2 fingers moving in perfect sync. Pretty smart.
Okay, we've covered the high-level plan, the arm's precise position, and the gripper's mechanics. But now we're going to go one level deeper, into the invisible forces that make it all work, the physics of contact. You see, in a simulation, a robot doesn't actually feel anything. We have to explicitly tell the computer what happens when 2 objects touch.
And one of the most important parameters here is friction. It's not just a single number either. In a physics engine like MuJoCo, it's actually a set of 3 values that control how much the surfaces resist sliding past each other, spinning against each other, and even rolling. Getting these values dialed in just right is absolutely key to a stable grasp.
For this particular task, the engineers landed on a sliding friction coefficient of 1.5. Now, you're probably looking at that number and thinking, okay, 1.5, so what? Well, that specific number is literally the difference between success and failure. Let me show you why.
It's because a value over 1.0 gives the friction pads on the gripper enough tangential grip to fight against the 150-gram weight of the box. If this number were just a little lower, maybe 0.8, the box would just slide right through the fingers the moment the arm tried to lift it. Game over. That single parameter is holding the entire operation together. But it's not just about friction. It's a whole orchestra of parameters that all have to be in tune. This table really shows what a balancing act it is. For example, if your contact dimensionality, condim, is too simple, the box might start to rotate in the grip. If your contact's softness, solimp, is too soft, the fingers will look like they're squishing right into the box. But if you make it too stiff, the whole simulation can become unstable and just break. It's this delicate process of trial and error to find that perfect harmony.
You know, when you see that final, perfect, successful grasp, you're not seeing the first attempt, not by a long shot. You're actually seeing the end result of a long process of discovery, of finding and fixing all the little things that can, and definitely do, go wrong along the way.
And this is where the real learning happens. For instance, the engineers found out that a 180-degree orientation error could totally fool the IK solver. The solver would think it had succeeded, but the gripper was pointing in completely the wrong direction. They learned that when calculating a pose on the opposite side of the robot, you have to give the solver a little hint by mirroring the shoulder angle. Every single one of these points represents a bug that was found, understood, and squashed.
So ultimately, that seamless motion we saw at the very beginning, it's kind of an illusion. The reality is a stack of carefully engineered solutions. You have a high-level 11-step plan, you have hyper-accurate IK calculations for the arm, you have a mechanically clever gripper design, and you have a finely tuned model of contact physics, all working together in concert.
Now, think about this. This entire pipeline was handcrafted for one specific box in one specific location. But the real world is messy. It's unpredictable. It's filled with millions of objects the robot has never seen before. So the really big question for the future is, how do we get from this perfectly scripted dance to a robot that can truly learn, adapt, and grasp anything, anywhere? That is where AI comes in, and that is a story for another time.